Dear students, I am very happy to welcome you to our first lecture in machine learning this semester. It is not only the first lecture this semester, it is the first lecture at all. So this semester I decided to offer this course, and for that purpose I also dropped the two other courses I have given so far. It is the business forecasting lecture for master students and the quantitative methods in finance. Why I opted for the machine learning? First, it is a very hot topic with many new and influential methods in practice and also in academia. But also, maybe some of you also took also the course on data mining during your bachelor studies here in Augsburg, and I was really impressed how important and how popular the course was among our bachelor students, despite of the fact that it was given by a statistics professor and despite of the fact that there were plenty of formulas on the slides. Um, the fact that I give this lecture for the first time has also some consequences. I'm pretty sure that there would be plenty of typos and some parts that I would change for their next year students. But it is like human learning as an alternative or like opposite situation to machine learning. So sorry for the typos or for all the errors that we will find together on the slides during this semester, but all of them are just my bad, but learning by doing. What are we going to discuss during this course? You know probably that this semester is 1 week shorter. Moreover, I invited an expert in machine learning in practice to give a guest lecture during this semester. He will also record his lecture and provide us with their video. We'll discuss all possible application that he is doing with machine learning in his startup here in Augsburg. So because of that, our semester or the stuff we can discuss is going to be pretty short or very condensed. We'll start with the supervised learning. The supervised learning we'll discuss in a couple of slides, but we'll not concentrate on a particular method. We'll try to do it in a more or less general way. Then we'll move to the methodological part. We'll talk a lot about the regularization and feature selection. We'll talk about regression trees. That's something what you probably know from the data mining course. We'll talk a little bit about neural networks and deep learning. We'll also introduce some very popular and innovative ideas such as support vector machine and Bayes classifiers. The last two items in the supervised learning are really extremely hot topics nowadays in practice. It is about ensemble methods or about super learners. It is the way how can we combine different methods or different approaches to a single large model. And finally, what is really on demand nowadays is the interpretable machine learning, how to learn something what human can understand from complicated machine learning algorithm. Then we'll move to the second part, to unsupervised learning. We'll discuss it in a second. Some parts of that you probably have seen in the data mining course if you have taken that. It's about clustering, but I also will introduce topics which go far beyond what we have discussed in that course. So don't worry if you haven't taken the data mining course, you will not miss anything. Now, depending on the time we have and depending on my speed, I would like to give one lecture on reinforcement learning. It is the third part of the machine learning, like supervised, unsupervised, and reinforcement learning. You probably know that all those computer games, they are tested or evaluated using reinforcement learning tools. Finally, we'll talk about text mining. Text mining is extremely popular, say, for the evaluation of news, for evaluation on natural language or natural language processing, how it is called in machine learning. And finally, if we have time, we'll shortly come to image processing. We have a couple of projects that share research projects on image data analysis, and I would like to share with you some basic ideas of their image processing, including their convolutional neural networks. Please note that the course in machine learning can be taught at a very different levels. If you take this course at the Faculty of Mathematics or some Faculty of Natural Sciences, probably you will talk a lot about very theoretical concepts such as information theory, how we process information, how can we quantify information. You'll probably also talk about the convergence problems of many machine learning algorithms and so on and so forth. If you take this course at the Faculty of Information Sciences or IT faculty, probably you'll concentrate on programming, on the algorithmic perspective of machine learning. So what is the most efficient form, or what is the fastest algorithm to train a neural network? We'll take here the middle path in some sense. We'll try to be formal enough to realize how the methods work, but we'll also try to get some more intuition why the methods are as they are. So probably my way of giving lectures. We can have one formula. I can discuss it like 15 minutes, so that everyone really realizes what is hidden behind that and why the formula is as it is. We will also talk a little bit about the computational part, but we are lazy in that perspective, so we'll typically take the functions which are already provided in their software and apply those functions to their data at hand. I think this middle path, a little bit of theory, a lot of intuition, and their programming perspective is exactly what a student in business economics needs. So he is exactly at their cutting point of different fields like quantitative, IT, and business economics, and we'll try to follow exactly this path in the course. This is the formal slide. All the lectures will be provided as videos. Also, the PDF slides will be uploaded to DigiCampus. If you have any questions, just feel free to use the form function in the DigiCampus. You can write also the emails directly to me, but it would be better if you have some particular question to the lectures to post it on the forum, so that your friends can also have a look at their questions and at my answers. I'll try to reply as soon as possible. If you have any further questions, you can contact also Jonathan Fader. He is responsible for their exercise classes and for their tutorials. All the information on their tutorials you can find on the webpage and in their DigiCampus. The exam, this is still an unsolved problem. I believe that the exam is going to be exactly as it was this summer semester, so everything is going to be face-to-face, no digital or online exams. For that case, our exam is going to be a 60 minutes exam, open book, so we can use whatever you want. The structure of the exam is going to be similar to what we've seen in their econometrics, for example. So it's a lot about their intuition. It's a lot about understanding their the models, and it's also about understanding the output from the software. So no proofs, nothing like that, and you can take whatever you want. Regarding software, we used R in the econometrics course. We also used R in all the bachelor courses, if you took your bachelor here in Augsburg. For that reason, I think it is convenient to work with R also in this course. In fact, the software is not that important here. It's more about understanding what we are doing. For example, if you want to fit an elastic net in R, then there is a function glm net. You can just check the help for glmnet and see that it can train elastic net. If you do it in MATLAB, then there is a lasso function, and you provide the function alpha, which actually specifies your elastic net. And in the Python, there is a function elastic net, and you also provide some alpha. So in fact, how you write this function is really irrelevant. The main point is that you understand what the elastic net or lasso or ridge regression is. I gave a course on random forests, I think last year, to people coming from industry. So I went really through all the theoretical parts, the implementation examples, and so on and so forth. And then one of the guys came to me after the lecture, said, "Well, thank you very much for a very nice course, very nice lecture here. Finally, I understand what a random forest is, despite of the fact that we use this random forest already for a couple of months at our company." So people are just using some function from Python or from R without really realizing what is hidden behind that. It's not that bad, but I think they can do much better in terms of forecasting, in terms of performance, if they really realize what is happening behind, what all those parameters mean, and how their model looks in general. Now, what is machine learning? I think there's not much what I can explain. You can just Google for machine learning and go, for example, to Wikipedia. On the Wikipedia, you will see that it is a study of computer algorithms that improve automatically through experience. So it is a very general definition. That's why the whole field is called learning, and that's why we'll talk a lot about training. So what really happens, the machine learning algorithm builds a mathematical model or mathematical or statistical model using sample data. And it tries to build it in such a way that it can be generalized to new data, to test data. And all those algorithms are very general. They are not really tuned to work with particular type of data. They are not really tuned to work with particular data sets. They can be applied to very many different types of data. This is really the advantage of those methods. You can take, say, a random forest and apply to any type of data. Let's say not really any type of data, but there are some constraints. But nevertheless, you will get some pretty good output at the end. Why shall I do this course? I'm professor of statistics, but in fact, machine learning is very closely related to computational statistics. You will see during the course that many topics, many ideas, they actually stem either from econometrics or from the basic statistics with very, very tiny modifications of those things. If we move in completely business or economics area, then what we are going to do here is something like predictive analytics. Most of the machine learning algorithms are aimed to make nice predictions. So it's more about predictions. And that's why, from the perspective of the practice, it is called predictive analytics. The picture on the left-hand side is actually shows where the machine learning is located. It is like intersection of statistics and mathematics. So that's what you have. It's an intersection of computing. We have some basic knowledge of R, and we'll try not to dive into their IT perspective of machine learning. And you need some domain knowledge, and business economics is exactly what you bring with you. So this intersection is a perfect constellation of those three parts you have already from your background during your master studies last 2 semesters and from your bachelor. Now, it's not a surprise that machine learning has very many different applications. We can talk about something very simple, medical diagnosis, for example. We try to predict if a particular person relying on their blood tests, blood pressure tests, and so on and so forth, is really healthy or is the person ill. So if you really did a blood test with like 50 or 60 different elements or items on the list, for a human being, it is really not always easy to extract all the important information and to correlate their exceedances or like bad values in the test to a particular disease. For machine learning tool, it is much easier. Of course, we have an ethical perspective of all that. Is it really correct to assign a computer to make diagnosis? What happens if their computer is wrong? What happens if if the algorithm misses some kind of disease? Who is responsible for that? Stock market trading. There is a lot of discussion nowadays about high frequency trading. It is trading on their millisecond basis. It is clear that human being cannot react that fast to any changes on financial markets, and it should be a very smart computational algorithm that can handle this kind of speed and can handle this amount of information flowing on their, like swimming on the financial markets. Online fraud detection can be online fraud detection, but it is can be very simple fraud detection. For example, consider their financial authorities. If you submit your tax report every year, you can apply a machine learning algorithm to detect if there is something wrong, something suspicious in your tax report. We can also talk about, say, image recognition. You know, plenty of those nice pictures on their Facebook with dogs and cats. If the algorithm can identify a cat, or it can identify a dog, or it's something mixture of the two of them, everything is based on some image processing and convolutional neural networks. Speech recognition, exactly the same. So either you have a native speaker, then no modern algorithms can handle it pretty well. Or you have someone like me, my German is as bad as my English, and still a computer algorithm or machine learning tool is able to decompose their sounds I make into complete sentences. Self-driving cars, traffic prediction, all those fields are really something where their machine learning tools can be applied. You see their fields of applications are very heterogeneous. The methods are in fact very, very similar. That's why it is a general purpose algorithms, what we are going to learn here, and they can be applied to very heterogeneous and um, like different types of data. Now they're splitting into unsupervised, supervised, and reinforcement learning, as I've discussed just on the second slide. It is a classical separation of the machine learning. The supervised learning, it is like the oldest one. It is mostly related to the classical regression. You see the regression place here, the central row with all the possible applications. Then we have a classification. That's what we did with the logistic regression in their econometrics course. And then we can switch, for example, to unsupervised learning, clustering. That's something what we have done in the data mining course, but we'll go on with that in this course as well. And what is really important nowadays is the dimension reduction techniques. So we have huge amounts of data. No one can handle that amount of data, and it is not really important and necessary to handle all this type of data, all this amount of data. So what we can do, we can try um, uh, to make a short or smaller data sets in some sense without any informational loss. So dimension reduction is about reducing the amount of data without losing a lot or much information of that. And then there reinforcement learning. It is really about real time decisions. It is used for games AI, artificial intelligence for games. It is used nowadays also for financial applications. It's really used almost everywhere. Fortunately, we'll have very short part because we have to start with supervised, unsupervised, and then at some point we'll come to their reinforcement learning. Now, let's try to disentangle the supervised, unsupervised, and reinforcement. I discuss here only supervised and unsupervised, and we skip the definition and the idea of the reinforcement to a later point. So how the data is structured and how it is called in machine learning. Typically, we have one output and or target variable yi. So you notice that the notation or the concepts here are slightly different from what we had in the econometrics course. In the econometrics, we talked about regressor, regressant, dependent variable, explanatory variable. Here we talk about target variable. That's what we try to model. That's what we target. It can be univariate or multivariate. That's also something new. In the econometrics course, our y was always univariate. And the extension to multivariate WiSe is really complicated, and it is never considered in the classical econometrics lecture. So here for machine learning, we can take a multivariate output without any need to adjust or adopt their algorithm. So we call this kind of a data labeled data. Why it is labeled? Because we know the value of yi. Let us refer to the CO data from our econometrics course. I will use this data from time to time because you know it. I don't have to explain what variable is responsible for what. So our salary was our target variable, our output variable. It means that every single person in our data set was labeled. So every CO had a label. On this label, there was their salary written. So our objective is to predict or to make a forecast about those labels for new COs. So the aim of supervised learning is using the available data, the training data, to predict the target variable or predict the label for a new observation for a new data. Now, what do I mean by the available data? On the one hand, we have our labels, we have our yi's, but we also have our features, our xi's. So again, in the econometrics course, we talked about regressors and explanatory variables. Here we talked about features or about inputs. Notation is the same, so xi is always a feature, yi is always the target variable or the output. Those variables or those features are mostly multivariate or on mixed scales. They can be binary, they can be ordinals, they can be categorical, that can be whatever you want. And this is called the input space. So data matrix in some sense is called there in machine learning the input space. That's what we had on the right-hand side, right-hand side. All those features build our input space from the perspective of machine learning. So again, we have labeled data. All the observations, like every single CEO has its own label, his salary. And the aim of supervised learning is to predict this label relying on the training data set for a new observation for a new person. Now, can we just group those possible tasks? Because supervised learning is very wide field. One possibility is to talk about regression like modeling. So it's like linear regression in the simplest case, but it can be also a regression tree. It can be a neural network. It can be whatever you want. Given new values for the features, so we have some x new, we would like to predict the output. So we would like to make a statement about y new. This is in the case if our y has an metric scale or cardinal scale, like salary, body weight, sales, temperature, body height, whatever you want. Classification is something different. That's what we did with the logistic regression. We know that y belongs to one, two, or many classes, and relying on their values of x new, we would like to classify or to assign the new observation to one of known classes. So those known classes, it's important here. So we know the classes like good, bad, clients as we had in the econometric scores, these bank data. Either someone buys a product or not buys a product, it's also a classification problem. Or we can also classify or like forecast their ranking of the companies. For example, we know we have triple E, we have a double E plus, and so on and so forth. It is also a kind of an classification problem, but not with two classes, but with many classes. So relying on all the information about the company, we can say, well, it belongs to triple B, or it belongs to A plus, or it belongs to C minus. And finally, the most complex one, but still a very important field of machine learning is the density estimation. Given X new, we make a statement about some conditional density of Y, or more generally about some probabilities related to Y. In the simplest case, what is the probability that the given company is going to be classified into a triple A? What is the probability that it's going to be classified to C minus? So it's not really the density, but it's some kind of probability function of our Y. If you talk about unsupervised learning, then it is like difficult to formalize. It is typically done for unsupervised learning. Typically, we would like to classify unlabeled data. So unlabeled is important here. We don't have Y. Oops. We don't have Ys. And we try to classify our data without Ys to some unobservable groups. So we don't know the classes. We just have the data and try to classify our data to some groups which we create on our own. So we try to extract those groups from the data directly. We also try to find some structures and patterns in the data. For example, if you see a picture of a cat, you know it is a cat. But how a computing algorithm can decide that it is a cat? So we need some kind of pattern in this data to recognize this collection of pixels as a cat. Or when you upload a picture to a Facebook, typically Facebook automatically suggests this is your friend, this is your father, this is your mother, and so on and so forth. How does it work? It's also about patterns. So there's some similarity between their face on this photo and the face of your friend, for example, on in his account, or how Face ID works on your iPhone. It's also a similarity between your face and their face stored in your iPhone or in your smartphone. Now I have to, it works. Finally, their unsupervised learning is also suitable for analyzing relationships between observations and or variables. So it's not only about extracting some information about a picture or about some data set, it's also about some movements or trends in the data. We'll not really talk a lot about that in this course, but I just skip it for the completeness of the slides. Now, what is the difference between statistics, econometrics, and machine learning? The common aim is always the same. We try to find some function f, which links our input space or our features to our target variable or to our output to y. Now, the difference lies in their approaches to finding this f. In the econometrics, we try to find a very problem-specific function f. So we fixed the model. It was a linear model, and we tried to calibrate the parameters so that we fit our data set as good as possible. All the deviations from the model or from our linear function were ignored. So we tried to minimize those errors, but in fact, we believe that those errors are just noise. There is no information in the random variables or in the residuals. It is typically done for small samples. It is not realistic to fit a linear model, or it is technically possible, but not informative to fit a linear model to a very large data set. Finally, their main objective was to fit it to a small sample and to make inferences for the population. So population, it was our penultimate goal. We believed that there is some population and we can infer something from their sample we have to that population. How we did that? We made some tests. So test if beta is equal to 0. It is in fact a test about the population parameter. So we believed at the end that this particular variable has no impact on y. Confidence intervals, it's also something about population. So in this interval must their true parameter lie at the end. We also focused on the explanatory modeling. If you recall our econometrics lecture, we spent like almost 2 lectures talking about the interpretation of the linear model. How do we interpret betas? How do we interpret betas if y is in logs? How do we interpret beta if x is a dummy variable? So it was a lot about the interpretation of the model and what we can learn from the model in economic terms. Now, the machine learning is not so curious about the true functional form of f. So it tries to find to approximate our f with as few assumptions as possible. So we don't specify any functional form of f, but we try to get it in some way from the data. That's what we have on the next slide. It is typically a very general purpose algorithm, and the main aim is to find some generalizable predictive patterns. So we try to find such peculiar forms or such peculiar dependencies in the data that are generalizable. It means you can apply the same model to another data set, to a new data set. And predictive, because we try to forecast all the time. We are not so interested in finite sample modeling or explanatory modeling for a given sample. We try, or we believe, to find a model which can be applied to a new data set, and the performance for the new data set is going to be good. So 2 typical features. Typically, we have only point forecasts, but those are very good. So it is extremely difficult to get a confidence interval, for example, using random forest or using neural networks. Typically, it's only about point forecast. Point forecast, that's something what we had in statistics too. And second point, their main focus lies on predictions. It's not about explanatory modeling, it's about predictions. Our main aim is to find a nice prediction for our target variable, having some new values or new instances for our features. Now, why it is called learning? So why it is called machine learning, not like machine algorithms or whatever? Because in econometrics, we have specified our f. We said, well, f must be linear because it's easy to estimate. In machine learning, we do not specify f. We try to learn f directly from the data. So we take our data and try to use the data to build um, our function f just step by step. It also it's also performed in some sense automatically. So it's not automatically that the computer does it in some sense, but there are some iterations, and those iterations they improve our function f step by step, relying on some test data set, some new data sets, and so on and so forth. So if you just let the algorithm run, you will get a good prediction or a good approximation for the model f. You probably have heard about those epochs, or how many hours a computer needs to learn to play chess or something like that. That's about this automatic learning. So you let or you run the algorithm for a longer period of time to play the same game or to train itself, and it will learn almost automatically. So learning is, as a summary, is about finding a model which is sufficiently good for their training data set, for the data at hand, but it also shows a good performance for out of sample or for test data set. So that's something what we don't have in kinematics. Kinematics, we are concentrated on our R squared. R squared was our main aim, to get high R squared. By high R squared, it is in sample performance, how good you can tune your model to their data at hand. In machine learning, it's not only about the data at hand, it's also about new data. This performance of the new data is called generalization, how the model can be generalized to new data. So it implies that this learning is not the same as fitting. Fitting is to tune your model to the data at hand. Learning is to find such a model that it will work for new data as or almost as good as for the old data. So what is a learner? Learner, it is a statistical and mathematical algorithm that uses the data to approximate f. So if you summarize all these automatically iterations, generalizations, and so on and so forth, at the end you will get a learner, a method, or an algorithm which learns this function f from your data. Now, a couple of years ago, machine learning was like well criticized because it was like a black box. Most of their pictures about machine learning was really a black box inside. You get some input data, you get some output, some forecast, and you don't know what happens in there. Why it is like that? Because machine learning consists of a huge number of different approaches. Everyone tries to improve those methods, to tune them a little bit. So at the end, your complex function f cannot be comprehended by human sense. You cannot really realize what happens with this function, how it looks like. In contrary to the linear model. Linear model, you have some feeling for that. Here, the function is so complex, for example, in deep learning, there are no chances that we can realize what happens there. This gave a rise to a new field of research in machine learning, which is called the interpretable machine learning. So interpretable machine learning is a set of tools, of methods, which helps you to extract some information from a machine learning algorithm, which can be interpreted by humans in a proper way. So we'll discuss about that, like with those limes and Shapley values during the lecture, but it is really an ongoing process nowadays to find interpretable machine learning algorithms and to deploy them reasonably. Now, the mathematics behind all those things is extremely complex. This is the next reason why it is frequently called a black box tool. So it's not just the function like deep neural network. It is a huge, complex mathematical algorithm behind there. Why it is like that? Because uh, if you minimize something, you have to compute derivatives. Those derivatives must be implemented. How to do it numerically, how to do it analytically. So there are many of those intermediate steps in every machine learning algorithm which has to be formalized with formulas, and that has to be programmed afterwards. And this complex mathematics typically leads to their conclusion, yeah, it's very complex, it's like a black box for me. It is really mathematically very complex. We'll try to explain the intuition with just a few formulas without really diving into their mathematical aspects and fine parts of machine learning. We'll just look at the functions and in R or in Python if you wish. And if you know the ideas behind the method, it is much more easy to choose, for example, the correct options or the parameters in the R or Python functions. So knowing the background there, methodological background of the method helps you a lot to tune your function, to tune your model appropriately.